Hello and welcome to Energy and Heat Part 2. This is going to be the more math-oriented section about energy and heat. We're mainly going to be dealing with this equation, Q equals mc delta T. So a couple quick notes about this. I just want to go over what each part is. First off, Q is going to be the energy that we're talking about. It's going to be measured in joules, capital J. Over here we have m, which is mass, so that's how much an object weighs on Earth-ish, give or take. And that's going to be measured in grams. All right, lowercase g here. So after that, we're going to have C, which is going to be specific heat capacity. And that one I'm going to explain in a bit, and that's going to be measured in joules per gram degree Celsius. And lastly, we have this one that's kind of joined together, and I'm actually going to go over this one first. We call this delta T, which strictly refers to the change in temperature. Now, the change part comes from the delta, and the temperature comes from the T. So delta T is a change in temperature. We usually figure this out by just taking the temperature final and subtracting the temperature initial. And this is also going to be measured in degrees Celsius. We're going to be using Celsius for this. So with that said, I'm going to take a brief aside to talk about specific heat capacity. So what is it? Well, specific heat or specific heat capacity is basically the amount of energy to heat 1 gram of a substance 1 degree Celsius. So, for example, water has a C of 4.184 joules per gram degree Celsius, which means it takes all about 4 joules of energy to heat 1 gram of water 1 degree Celsius. A couple other things like iron. Iron has a specific heat capacity of 0.450 joules per gram degree Celsius. Lead has an even lower heat capacity of 0.129 joules per gram degree Celsius. And as we look at other elements, honestly, metals usually have very low ones. We can get a whole bunch of different ideas of how much energy it takes to heat something. So this is super, 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 super important. This is what governs a lot of the things and a lot of the choices that people make when building things or making things. For example, a frying pan. If you want your food to get hot quick, you want something that can take very little energy to heat up. And that's why you generally make frying pans out of metal. You get your nice pan and you cook your eggs in it or whatever. And that pan is made out of metal, which has a low heat capacity, which means when you go ahead and put your fire under it, gosh, here comes my drawing skills. This is going to get hot quick because all of that energy from the fire can be turned into heat, heating up the metal. On the other hand, something like water has a very high heat capacity. 4.184 is pretty darn high. It means it takes a lot of energy to heat water, which might be why, for example, if you've ever been in a pool, those are hard to keep warm or hard to heat up because there's a lot of water and it takes a lot of energy. anyways, with that said, we now have these values. We know what they can do. So let's just go ahead and do some math. So in the morning, I like to make coffee. For some people that make coffee, sometimes you've seen this little thing called a French press. It's kind of got this like little stopper, and it has this thing in there, and you kind of push it down, and you have all your coffee in there and a little spout, and you get a nice cup of coffee. Now, I gave you all this information for no reason other than it's flavor text, but for my French press, I like my water to be at 80 degrees Celsius. However, my sink only puts water out at 25 degrees Celsius. So the question is, how much energy do I need to heat 200 grams of water to coffee temperatures? So we're going to solve this by just kind of filling in our equation, Q equals MC delta T. Now, the first thing that I want to talk about is Q is our energy. So this is what we're looking for. M, we've just been given, it's 200 grams. Now, specific heat is constant. So we can just look it up and, well, hey, look, I have it right there, 4.184 joules per gram degree Celsius. And lastly, I have delta T. Now, I want my final temperature to be 80, and my initial temperature is 25. So 80 minus 25 is going to be 55 degrees Celsius. So when I go ahead and just plug all this in, 200 times 4.184 times 55. And one quick thing to note is grams will cancel with grams, degrees Celsius will cancel with degrees Celsius, and we will be left with joules, which is what we want for our equation anyways. So all we have to do is go ahead and plug this into our calculator. And we get that the energy that we need is going to be 46,024 joules of energy. That is quite a bit amount of energy to heat up my coffee. But that's all there is to it. We can go also backwards. So let's say I overshot. My coffee water is too hot. Turns out I put more energy in it than I needed to, and now it's 95 degrees Celsius. Oh no. I want to cool it down to 80 degrees Celsius. And guess what? I still have 200 grams of H2O of my water. So now when we go ahead and plug it into our equation, Q equals mass, which is still going to be 200 grams, specific heat, which is still going to be 4.184 joules per grams degrees Celsius. And now I'm still doing the final temperature, which is 80 degrees Celsius minus 95 degrees Celsius. One concern you might have is you might say, hey, Mr. Garcia, what's up? This is going to be negative 15 degrees Celsius. How do I work with that? And the truth is you just do. Just plug it right in. So we're going to do 200 times 4.104 times negative 15. Our units are still going to cancel, and we're still going to get joules. So our final answer, Q equals negative 12,552 joules. And so you might say, well, what does this negative mean? Well, in this case, before when we had a positive, well, let's just do it this way. We had a positive, we were putting energy in. Now we have a negative. So it's just the opposite. We are taking energy out. So that's all there is to it. The last major thing I'd like to talk about is the second equation I mentioned from the previous lesson. This guy right here, Q equals M delta H. And I said that's going to be what we use to describe the flat parts. So let's take a look at that. In this case, so we're going to be looking at Q equals M delta H. So if we go ahead and look at an ice cube, pardon my slow drawing, and this ice cube is unfortunately starting to melt. Well, we're gonna need some values first. We need a mass. This is still mass. And so let's say we have a 12-gram ice cube. And this 12-gram ice cube, we want to know how much energy will it take for the full thing to melt. So if we want a just big puddle with no ice, the question becomes, how much energy is needed for the ice to fully melt? And we're going to have to use, because we're going from solid to liquid, we are going solid to liquid, we're going to have to use heat of fusion. So regardless of if we're going solid to liquid or liquid to solid, anywhere in there, we're going to be using heat of fusion. I'm going to actually reference that as delta H with a little f for fusion. Otherwise, it would be V for vaporization. And with each material, delta H is constant for each material. So basically what I'm saying is, look it up. Just look up the delta H. It's that simple. In our particular case, delta H fusion for water is approximately equal to 334 joules. And that's going to be specifically 334 joules per gram. So we'll finally go ahead and take this number, we'll plug it into our equation, Q equals M delta H F, or 12 grams times 334 joules per gram. You'll notice our units like to cancel out. And for this ice cube to fully melt, we will need 4,008 joules of energy to be put in. And that's it. These can get definitely more complex. For example, if we are looking at water, or sorry, if we are looking at not just water, if we are looking at a block of ice, so we'll actually take this whole scenario we had before. So if we're looking at this block of ice and we're going to say it initially starts at negative 20 degrees Celsius and it's going to end at 45 degrees Celsius, I'm not going to solve this whole thing, but I'm going to show you how to do it. You actually need to take it in 3 steps. 3 steps. So the first one is you need Q equals mc delta T for the ice as it goes from negative 20 degrees Celsius to 0 degrees Celsius. So that's step 1. Step 2, you need the Q equals m delta H of fusion as it goes ice to liquid. And that's going to be 0 degrees Celsius the whole time. And then step 3, you're going to need to look at the water using Q equals mc delta T once more as it's in a liquid state. And that's going to be as it goes from 0 degrees Celsius to 45 degrees Celsius. So these problems can get complex in that there are multiple steps in them. But if you look at it, each individual step is just one small Q equals mc delta T or Q equals m delta H. And while this may seem challenging at first, this is just going to be multiplication the whole time with nothing new. We will always look up our specific heats and our heats of fusion. And that's about it. I hope this helped and have a great night.